Hi everyone, this will be your video for series and sigma notation. This follows up on our few weeks about sequences, where we were learning about geometric and arithmetic sequences. We'll now be taking a step further and creating series. So you can follow along on your guided notes. There'll be examples, there'll be practice problems, and your homework problems that you should be completing as well. So first we have just the definition of what a series is. So here we go. We have a series is the sum of consecutive terms in a sequence. So essentially what we're going to be doing here is we're going to be doing a lot of addition. We're going to be doing a lot of adding here. So you can see, for example, A, we're going to take 1 plus 2 plus 3 plus 4. Okay, and that's the end of that sequence. There's no other terms, there's no dot, dot, dot. This is it. So we add up these numbers and we'll get 10. Easy peasy. So now looking at B, it's a whole different story here. If we look at B, we do have a dot, 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 right? So that means that our sequence is going on, forever. And each number we're adding is going to be greater than the last. So that lets us know that this is going to be getting pretty big, and we're just going to keep adding numbers to it that are even bigger. So we can just say this is our biggest number possible, which is infinity. And for C, this one's also a little different. We have this dot, 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 meaning it's going on forever. But now our values are in half of the one before, right? We have 1/2, then we have 1/4. That's half of 1/2. Then we have 1/8. That's half of 1/4. And we have 1/16. That's half of 1/8. So these values are all going to get smaller. These will actually all combine into 1. And I know that doesn't make too much sense, but we will get to that at some point. So don't be too hung up on B or C here. So let's talk about a partial sum. Okay, we use this symbol, capital S sub n, to represent the sum of a sequence. And it's going to be the sum of a specific number of terms. Okay, meaning that they're going to say find S sub 2, and that's actually what we're going to be doing. And that means we're going to use the first 2 terms. S sub 5 would be the first 5, and S sub 7 would be the first 7. So let's do this example. The first 2 terms are 3 and 6. We add them, we get 9. That's our answer. The next part of this example is asking us for S sub 5. So we're going to take the first 5 terms of our sequence. So we have 3 plus 6 plus 9 plus 12 plus 15. We add them up and we get 45. Now for the next one, it's a little tricky. They're asking us for the sum of the first 7 terms, but if you notice, we only have 5. But if you do look, you can see that each term is found by adding 3. So we can figure out that our next one would be 18, the next one after that would be 21, 24. You could keep this going even more, but we just need the first 7. So it's going to be the 3, 6, 9, 12, 15. It's our first 5. Then we have 18 plus 21. And when we add this all up, we'll get 84. So we do have a more streamlined way to solve for this, and that's using sigma notation, which is just below. Sigma is a Greek letter. It represents a sum. So we still use the symbol of S sub n. It's meaning the sum of a certain amount of terms. And we're going to be able to use this sigma notation. So we're going to start at the bottom, and we're going to fill in these blanks working up. So we're going to start here with this I. I stands for your index. Okay, essentially that's just the variable we're working with. The next thing that we have a line pointed to is this one, okay? And this one's going to be called our lower limit. And our lower limit is really, it's going to be our first term number. Okay, in the middle here, I'm going to make a little correction to a typo. This should be A sub I. And in the middle here, we'll be able to say that this is our rule for our sequence. And then the last thing that we can point out is this value that's on top of our sigma, and that's an n, and that's going to be our upper limit. And that's going to be our last term number. So kind of like telling us where to stop. So let's use the sigma notation to solve this example. We want to write this in its expanded form, and then we'll find the sum. So we will be we'll be plugging in this 1, and we're going to plug it into our rule. So our rule is just k squared. So we plug in our 1, and then we're going to add whatever we get when we plug in 2. And we're going to add whatever we get when we plug in 3. And we're just going to keep doing that until we get to our upper limit of 5. So here's what it'll look like. So first we have our 1 squared. Then we plug in our 2. Then we plug in our 3. Then 4. Then 5. At this point, you're just solving, or you're just simplifying really, and you're just using your order of operations, taking your time, making sure you're not making any silly mistakes. So we have 1 plus 4 plus 9 plus 16 plus 25. You can use a calculator, you can add it all up, and you would get 55 to be your solution. So on the next page, you can see how I already have an example done out. So you can see we're plugging in starting at 1, because that's our lower limit. And I'm going to plug in every number until I get to 6. Once you do that, you can simplify, add them up, and you get 579. So we're going to do the same method for example 4. It's a little more complicated, so this is the one I wanted to go over piece by piece with you. So again, we're going to start by plugging in 1. We're going to have 1 times 1 plus 2. You want to make sure that you're really clear with your notation and you're really clear with the organization, so that when you plug in 2, you can see that it's clearly your second term now. You're plugging in 2. We can plug in 3, plug in 4, plug in 5, and then also 6. We stop at 6, that's our upper limit. So this one was tricky because not only are you plugging in n to the n plus 2, you have an n in the front of it as well. So you have to make sure you're plugging it into both pieces. Taking your time, this really looks like 1 times 3 plus 2 times 4 plus 3 times 5 plus 4 times 6 plus 5 times 7 plus 6 times 8. And then we can use our calculators or use what you know. We have 3 plus 8 plus 15 plus 24 plus 35 plus 48. You can add them all up and we'll get 133. You can always use the notation S sub 6 since we found our sum of our first 6 terms, and that equals 133. You can do the same thing up here as well. For example 3, you can rewrite this as S sub 6 equals 579. So let's look down at these next 2 examples. It's now the opposite. They're telling you that there's a series here. These are numbers that have already been added together. And we need to find the sigma notation for this. So this is our n value for each term. And remember, we're plugging in this n value. So we need to think, like, how can I get from 1 to 4? So I could just say, okay, maybe if I times this by 4, it might work. And then we could see if it'll work for the next term. So 4 times 2, that'll work. 4 times 3, that'll give us 12. 4 times 4, 4 times 4 gives us 16. And 4 times 5 gives us 20, so that works, okay? So what we can do here is we can think that whatever our n is, we multiplied it by 4. We'll draw our sigma. Now we have an n, so we're going to say that the number we stop at, and you can see that the highest number we have in our n, our upper limit, we stopped at 5. So remember, your upper limit goes up here, and the value you start at goes down below. So we started at our first term, and we went until we got to our 5th term. So started at 1 until we got to 5. Let's do the same thing for the example down here. So again, this is when n equals 1, 2, 3, 4, 5, 6. All right, this one kind of looks a little straightforward, right? We have 1 over 1, that could be it. 1 over 2, that's our n, right? That's 1 over 2. This is working, right? So anytime we do the 1 over our n value, these are all of our n's. Okay, so this is working. So that means that I could write this as 1 over n. We wrote this one up here as 4n because it was n times 4. So writing our sigma notation, this is kind of like all the pieces we need. We already figured out this was 1 over n. The term we start at is our first term, so that's a 1. And the term we end at was our 6th term, so we'll have a 6 on top. Put a box around it, and this is all done. So you can continue on the practice problems and the homework problems. If you need any help, just make sure you ask.